Hello again. New thing with lots more rules to remember. We're talking about oxidation numbers. In a molecule, even though we don't usually talk about charges, you can kind of talk about charges and say that an atom has a positive 1 or positive 2 or negative 1 or negative 3 or whatever oxidation state, which is how many electrons does it have on, within its sphere of influence in this molecule. And things that are highly electronegative tend to end up with low oxidation numbers because they attract extra electrons. We usually don't talk about it like they have acquired a charge, although I get lazy and do exactly that sometimes. It's better to say that it has a lower oxidation number or a lower oxidation state. So, really fast example, if you have something like ammonia, the hydrogens inside ammonia generally have an oxidation state of +1 each. There are 3 of them, so that means their total oxidation state, or their total, you could call it charge, I guess, is +3. But ammonia overall doesn't have any charge. So if the hydrogens are +3, the nitrogen must be doing something that makes the total come out to 0, and that means our nitrogen must be -3. So we'd say the oxidation state of nitrogen is -3, or the oxidation number is -3. The hydrogens are +1 each, and that explains why ammonia comes out to a total of 0. We give you a big stack of rules to learn for this. They're not as bad as they look at first. Most of them are things you might have guessed anyway. Pure elements are zeros. So if you have iron, that's a 0. If you have oxygen, both of those atoms are 0. If you have sulfur, all those atoms are zeros. If you have an ion, something like Cl-, the charge is right there. Just believe that number. Chlorine's oxidation number is -1. Or the chloride ion's oxidation number is -1. If you have an oxide ion, its oxidation number is -2. Easy. Now, the ones you're going to have to remember because we use them a lot, hydrogen is +1, except for a couple weird exceptions that don't come up very often. For now, when you're just starting, lock this into your head. Hydrogens are +1s, basically always. And oxygens are -2, basically always. Again, there are a couple weird exceptions, and they might come up a little bit later, but mainly we're going to use these 2 things. So just let me give you an example before we kick off with the practice. If you have something like H2SO4, here's how you'd go about analyzing this. Looking at the rules, we'd say if there's pure elements, well, there aren't any, next. Monatomic ions, there are no monatomic ions here, next thing. Hydrogens are +1. So the first priority is we say each hydrogen is +1. I'm going to put +1 each, total of +2. Next thing in priority is oxygens are -2 each. So these oxygens are -2. I'm putting EA for each. There are 4 of them, so that's a total of -8. And now we come to sulfur, and you could look on the periodic table and see that sulfur ions like to be -2, but what's happening here is we're saying we need the total of all of these charges, or oxidation states, to be 0, because H2SO4 has no net charge. So sulfur, we're saying, we know you like to be -2, but we've already got +2 from our hydrogens, and we have -8 from our oxygens, and then we have whatever the sulfur does, and we need all that to add up to 0. In other words, the combined oxidation numbers for these, the H and the O's, are -6. We're saying, sulfur, we need you to get us to 0, buddy. We know you like being -2, but today we need you to be +6. And so sulfur ends up being forced to have an oxidation number of +6 because it's the only way to make this molecule work. And what that would mean is sulfur has given away 6 electrons, pretty much, to enable this molecule to hold together. That's the only way to keep this family all connected. So plus 2 from the hydrogens, minus 8 from the oxygens, and then you think, what would sulfur have to do to reconcile all that and get us to a total charge of 0? Hydrogen gets to pick its number first, oxygen goes after that, and then we get to the very last rule says the oxidation numbers in a compound must add up to the net charge of that compound, which is almost always 0 in our questions. So we'll practice that a bunch. You'll get used to it. These rules look pretty miserable when you first see them, but I think you'll be surprised how often these two will do all the work for us. At least I hope you will. I'll give myself a little more space. Okay. So this is H3BO3, and the B is in bold. They're saying we're interested in the number for the boron. That's the only one we want you to tell us. So remember, hydrogens are plus 1 each, so we have a total of plus 3 from our hydrogens. Sometimes I write plus 1 each and then plus 3, but I'm trying to save space. Oxygens are minus 2 each, so here we'd have a total of minus 6. So what does boron have to be to get us to a total of 0? If we wrote this in math, we'd write 3 plus B minus 6 equals 0. 3 minus 6 is negative 3. B must be 3. So the oxidation number for our boron must be plus 3, so that we get the desired total of 0. Not bad. Let's do it lots more times. Methane. First rule, hydrogens are plus 1 each, so 4 hydrogens must be plus 4. Carbon, we need you to do something so that our total ends up at 0. We're at plus 4 right now. Carbon says, fine, I'll be minus 4. Bromate ion. Oxygen, we don't have any hydrogens, so that rule gets skipped over. Oxygens are normally minus 2 each, so we have a total of minus 6 from our oxygens. So bromine, we need you to be something that will get our total up to, not 0 this time, negative 1. If we wrote this in math, we'd write Br minus 6 equals negative 1. Add 6 to each side, and you get Br equals 5. So the oxidation number for bromine is 5. Plus 5 minus 6 here comes out to a total of minus 1, just like it's supposed to. Okay, sulfite ion. Oxygens, 3 of them, total minus 6 charge. What does sulfur have to be to get our total up to negative 2? Think about that, or if you already got the answer, I will now check it using algebra, sorry. Sulfur minus 6 equals negative 2. Add 6 to each side. Sulfur must be 4. Think you're getting it? I'll do the next 3, and I'll start to speed up when we do the second column. Hydrogen carbonate ion, minus 6 from the oxygens, minus 2 each, and there are 3 of them, plus 1 from our hydrogen, and we don't know what the carbon is. You could write 1 plus C minus 6 equals negative 1. You don't have to write an equation. A lot of people can do these in their heads, but in case you want a system, here's what the system would look like. 1 minus 6 is negative 5. Add 5 to each side. C equals 4. MNO, this one will be fast. Oxygen is minus 2, but our total is 0, so the manganese must be plus 2. That was quick. And here's one that you could easily get wrong if you didn't know some little details. So let me just scroll back up to the rules for a second. H2O2 is hydrogen peroxide, and this is one of our little exceptions. All right, I have to zoom out a little bit. Right here. The oxidation number of oxygen is minus 2, usually, except in peroxides, where it's minus 1. H2O2 is hydrogen peroxide, so we have to adapt for this one. In this case, the oxygens are -1 each, and so their total is only -2. And there are 2 hydrogens, and we need our total to come out to 0. So what we have here is 2 hydrogens minus 2 must make 0. Add 2 to each side. The 2 hydrogens must be giving us a total of +2. Divide by 2. Each hydrogen must be giving us +1. So these hydrogens are +1 each. Upon reflection, we could have just looked up the hydrogen because there's a rule that says hydrogens +1 with some rare exceptions. That would have been another way to get this. Hydrogens are +1 each. In a peroxide, oxygens are -1 each, and then we wouldn't have even needed to calculate this. Just knowing it's a peroxide would be enough. Okay. VO2, some kind of vanadium ion. Okay, so oxygens are normally -2. We don't know what vanadium is, but we know our total is +2. So we have V, -2 from the oxygen, equals +2. Add 2 to each side, and we get V must be 4. The oxidation state of vanadium is +4. HNO2, -2 each for the oxygens, total of -4, +1 from the hydrogen. 1 plus N minus 4 equals 0. 1 minus 4 is -3. N minus 3 equals 0. Add 3 to each side. N equals 3. Oxalate ion. Here we have 4 oxygens, -2 each, so the total must be -8. 2 carbons -8 gives a total of, not 0, -2. Add 8 to each side. 2C equals 6. Divide by 2. Each carbon's oxidation number must be 3. Some weird xenon molecule that you don't see very often. -2 each for the oxygens, so total of -8. So we get our xenon number, whatever that is, -8 for the oxygens equals -6. Add 8 to each side. Xenon must be +2. L is a trap. Every question we've done so far, hydrogen has been +1, but this is another one of the exceptions. The oxidation number of hydrogen is +1, except in metal hydrides. Lithium hydride, sodium hydride, potassium hydride, rubidium hydride, those group 1 elements are basically where this happens. In those cases, the hydrogen goes negative. What should tip you off about that in this question is just that the hydrogen is written second. You know how in our compounds we normally put the positive ion first and the negative ion second, and we almost always put hydrogen at the beginning of our compounds because it's almost always a +1. The fact that we put it second here should warn you, wait a minute, something unusual is happening with hydrogen in this case. These 2 atoms met. Hydrogen said, hey, I'm pretty much always +1. Do you mind being a -1? Sodium says, I don't even know how to be -1. +1 is all I've got. +1 is the only trick I know. Hydrogen says, fine, I guess I know how to be -1. I'll do that for you. And so the oxidation state of hydrogen in this compound is -1 because sodium just cannot function any other way. This is the only ion it ever makes as far as I know. S2O6, I don't know what this is, but I know that oxygens are -2 each, so if we have 6 of them, that's -12. We have 2 sulfurs, and our total is -2, so we can write 2 sulfurs -12 for the oxygen makes a total of -2. And now pretend you're in math class, add 12 to each side. 2S equals 10. Divide both sides by 2. The oxidation number of sulfur is 5. And last one, this is some xenon thing. We have -2 from our oxygen, +1 from our hydrogen, don't know what from our xenon. 1 plus whatever xenon is minus 2 has to equal 0 because there's no charge given for this. 1 minus 2 is negative 1, so we get xenon minus 1 equals 0. Add 1 to each side, and the oxidation state for xenon here must be positive 1. Not too bad? Hopefully not too bad.